So this is a video to support a course that I'm teaching in number theory. This is the 11th such video. And here we want to look at a very classic theorem known as the Chinese remainder theorem. And this involves solving a system of linear congruences. So if you recall from linear algebra, you learned how to solve a system of linear equations. This would be like the congruence version of something you would do there. Okay, so let's see how the statement of this theorem goes. So we want to assume that we've got a collection of pairwise relatively prime natural numbers. So in other words, we've got these natural numbers n1, n2 up to nk, such that if you choose any two of them that are non-equal, their GCD is 1. Furthermore, you've got k integers, and your goal is to solve the following system of congruences for x. So you've got x is congruent to a1 mod n1, x is congruent to a2 mod n2, all the way down to x is congruent to ak mod nk. And this theorem says that this system has a unique solution modulo capital N, which is this product of the little n's. And we'll look at the proof, and what's great about the proof is it is a constructive proof. In other words, you can follow the method of this proof for any kind of such example, and you'll find an actual solution. Okay, so let's move on to this proof. So let's maybe set n equal to this product n1 to nk, as is defined in the statement of this theorem. And then we want to set capital Ni equal to capital N divided by little ni. And that's going to be true for I between 1 and k. So notice that this is going to be the product of all of these little n's except the ith little n. Okay, so now let's notice that the following statement is kind of obviously true. The GCD of capital Ni with little ni is equal to 1. So why is that? Well, that's because this capital Ni is a product of all of the little n's except for the ith little n. But all the rest of the little n's are relatively prime. So that means we've constructed this capital Ni out of numbers that are relatively prime to little ni. Okay, but now you should be motivated by all of the things that we've done with the GCD, especially writing the GCD as a linear combination, because that's such a powerful trick. So from here, we can say there exists xi, yi such that capital Ni xi plus little ni yi equals 1. So again, that's because we can always write the GCD as a linear combination. In other words, this is like using Bézou's identity. But now let's reduce this equation mod little ni and see that we have capital Ni times xi is congruent to 1 modulo ni. But that's not exactly the thing we want. We don't want a 1 over here. We want an AI over here, given what's in this purple box. But we can turn this into the right form just by multiplying both sides of this congruence by AI. So doing that, we get Ni times AI times Xi is congruent to AI modulo Ni. Okay, so now that we've brought all of these numbers into existence, we want to smash them together into what will be our solution to this system. So let's maybe go ahead and set, I'll just call it x equal to n1 a1 x1 plus n2 a2 x2 all the way up to nk ak xk. And that's the capital N's, not the lowercase n's. And I want to follow that up with the following observation. And that is, if I is not equal to j, then ni is congruent to 0 modulo nj, where this is a capital Ni and that's a lowercase nj. So how do we know that? Well, let's recall that capital Ni is really the product of the little ni's except for the ith. Well, let's recall that this capital Ni is a product of all of the lowercase n's except for the ith lowercase n. That means it includes nj as one of the terms in its product. So in other words, this capital Ni is a multiple of little nj, but that's exactly the same thing as saying that it is congruent to 0 mod little nj. Okay, so now where can we go from there? Well, now let's just fix some j that's in the set 1 to k, and we're fixing it arbitrarily. And let's notice that we have x will be congruent to nj, aj, xj modulo little nj. Now, how do we know that? Well, that's because everything not equal to j is going to go to 0 by this observation that we just talked through. But then by our construction, we know this nj, aj, xj is really just aj. So this is congruent to aj mod nj. But that's true for all j between 1 and k because we fixed this arbitrarily. So in other words, this number which we've constructed x satisfies all of these congruences over here. So it forms a solution to our system of congruences. Okay, so let's see. We've got a solution. Now we want to show that that solution is unique mod this capital N. Well, let's get rid of this and then we'll do just that. Okay, so on the last board, we proved that we indeed have a solution x to this system of congruences given the following setup. Now we want to show that that solution is unique modulo capital N. So we've got a solution x. Let's maybe go ahead and suppose that y is another solution to this system of congruences. Okay, well, the fact that x is a solution means that x is congruent to a1 mod n1 all the way down to x is congruent to ak mod nk. That's what we mean by saying x is a solution to this system of congruences. But then since y is a solution, that means that y is also congruent to a1 mod n1 all the way down to ak mod nk. Okay. But now what we can do is just subtract these congruences like one at a time. So we'll subtract x minus y and a1 minus a1 mod n1, do the same thing mod n2 all the way down to nk. So in fact, you want to think about just like grouping all of these together, and then doing some sort of subtraction. That's a little bit sloppy, but it's really not too bad. Okay, so that tells us that x minus y is congruent to 0 mod n1 all the way down to x minus y is congruent to 0 mod nk. Just by that subtraction. But that tells us x minus y divides n1 all the way down to x minus y divides nk. That's by the definition of congruence modulo n. Okay, well that doesn't quite tell us that x minus y divides this product n1 to nk. It tells us that x minus y divides the LCM of the numbers n1 to nk. So that's by the definition of the LCM. So let's write that down. We have x minus y divides the LCM of n1 up to nk. But now we can easily finish this off. Since these ni's are pairwise relatively prime by our assumption, that means their least common multiple is just their product. So that means that x minus y divides their product n1 up to nk. But let's recall that we called that capital N. We have x minus y divides capital N, which is the same thing as saying x is congruent to y modulo capital N. Well, let's see what we've got. We had the existence of a solution from the last board. We supposed that y was another solution. And we showed that those two solutions were equivalent modulo capital N. But that exactly is what we need to prove this uniqueness condition down here. Okay, so now let's jump into some examples. Okay, so let's start with the following example. We want to solve this system of three congruences. X is congruent to 2 mod 3, it's congruent to 3 mod 7, and congruent to 9 mod 10. Okay, so maybe the first thing to do is to calculate our capital N, which will be the product of 3, 7, and 10. So our capital N in this case will be 210. Okay, so now that we've got 210 for our capital N, we should calculate our N1, our N2, and our N3. Let's recall that N1 is capital N divided by little n1, or it's just the product of N2 and N3. So N1 here is 70, again, because it's the product of these three, except for the first one. N2 will be equal to 30 for pretty much the same reason, and then N3 will be equal to 21, again, just following that pattern. Okay, so now we've got our values N1, N2, and N3. And now built into the proof was the construction of this X1, X2, and X3. And we didn't really point it out super carefully during the proof, but now is a good time to point out that X1, X2, and X3 are the inverses of these numbers modulo these numbers. So just to reiterate that carefully, we have X1 should be congruent to N1 inverse modulo little n1, which is 3 in this case. So for our setup, we have this should be 70 inverse modulo 3. So that'll be equal to X1. So we need to calculate that. Well, what's 70 inverse? Well, maybe first of all, we should reduce 70 mod 3. Notice that 70 is one more than 69. 69 is a multiple of 3. So this is the same thing as 1 inverse mod 3. But then 1 is its own multiplicative inverse mod 3. So we know this is 1 mod 3. So all of this comes together to say that our X1 can be taken just to be the number 1. And now we'll play this same game with X2 and X3. So X2 should be congruent to N2 inverse. Well, that's going to be 30 inverse modulo little n2. Well, that's 7. Okay, but again, we want to reduce mod 7 whenever we can. So reducing 30 mod 7 will give us the number 2 because that's 2 more than 28. So this is congruent to 2 inverse mod 7. Now we just have to think about what is the inverse of 2 modulo 7. Again, you can do this with the extended Euclidean algorithm, but since 7 is pretty small, we can really just guess and check. So let's notice that 2 times 4 is equal to 8, but 8 is 1 more than 7. So that means 2 inverse is equal to 4 modulo 7. And then from this, we know our value for X2. We can take our value for X2 to be the number 4. Now let's keep going. So X3 must be congruent to capital N3 inverse. So that's going to be 21 inverse modulo little n3. So that's going to be 10. But this is another pretty easy one. Notice that 21 mod 10 is just 1. So this is congruent to 1 inverse mod 10, but that's just congruent to 1 mod 10. So now we can fit that in right here, that now we know X3 is equal to 1. Now we're ready to put all of this together to construct our answer X. So let's recall that X is equal to A1, N1, X1 plus A2, into x2 plus a3 n3 x3, where those are the capital N's. Well, we calculated those capital N's up there. We calculated the x's here. Let's just recall that the a's are these numbers. So 2 is a1, 3 is a2, and 9 is a3. So now we can just start putting all of that together. So here we have this is equal to 2 times 70 times 1. So that'll be a1, n1, x1. And then next we'll have 3 times 30 times 4. Okay, so we've got 3, 30, and 4 from that over there. And then finally, we'll have 9, 21, and 1. Okay, so now let's start adding all those together. So 2 times 70 is obviously 140. 3 times 30 is 90, times 4 is 360, and then 9 times 21 is 189. Now let's add all those up. 140 plus 360 is going to be 500 plus 189. That's going to give us 689. But we know our solution is unique mod capital N, which is 210. So that means we need to reduce this modulo 210. And that'll be kind of our nicest answer. So we can do that just with some fairly simple arithmetic, and we'll get the number 59. So 59 is our final value for x, which is our unique solution modulo 210. Okay, let's get rid of this and we'll do one more example. Okay, we're going to finish this off with a little bit more complicated of an example. So let's say we want to solve the system of congruences. X is congruent to 1 mod 4. It's congruent to 3 mod 10 and 8 mod 15. So let's notice that immediately we see something is up. The GCD of 4 with 10 is equal to 2. That's not equal to 1. And likewise, the GCD of 10 with 15 is equal to 5. That's not equal to 1. But that tells us that we cannot directly apply the Chinese remainder theorem. But we're actually in luck because there's a hack around this kind of thing in special cases. And this is one of those special cases. And so instead of solving this directly, what we'll do is work modulo certain prime powers. So we'll leave this x congruent to 1 mod 4 as is, but let's take this x congruent to 3 mod 10 and expand that into x being congruent to something mod 2 and something mod 5. You might say, well, why 2 and 5? That's because 2 times 5 is equal to 10. So I'll use this blue dot as a little key, and this blue dot is going to come down here. And notice that this splits into 2 cases. So this means that x is congruent to 3 mod 2, and x is congruent to 3 mod 5. But notice saying something is congruent to 3 mod 2 is the same thing as saying something is congruent to 1 mod 2. Because we only have 2 equivalence classes mod 2. Okay, so now let's do the same kind of thing for this other congruence. So I'll color code that in purple. So this purple dot will split again into 2 parts. We'll have x is congruent to 8 modulo 3, and x is congruent to 8 modulo 5. Again, because 3 times 5 is equal to 15. But now we can simplify each of those as well, just as we simplified above. So this is the same thing as saying x is congruent to 2 mod 3, because 8 is 2 more than 6. And here we have, this is the same thing as x is congruent to 3 modulo 5. Okay, so let's reiterate what we've done so far. We took this system of three congruences for which the Chinese remainder theorem did not apply, and took the second two congruences and wrote them equivalently as congruences modulo kind of the prime factorization of 10 and 15. Now we want to look at what we've got over here and see which congruences we want to smash together to form something that the Chinese remainder theorem will apply to. Well, let's notice we started with x is congruent to 1 mod 4, so we have to keep that one over here. Another thing we want to notice is that here we've got x is congruent to 3 mod 5, and here we also have x is congruent to 3 mod 5. So wrapped up in this blue dot and this purple dot is that x must be congruent to 3 mod 5. So we'll go ahead and keep that one as well. Now let's look at this right here. This says that x is congruent to 1 mod 2. In other words, it's an odd number. But let's notice that odd numbers are special cases of numbers that are congruent to 1 mod 4. So this guy right here does not actually provide any more information. So that means we don't need it in order to finally solve our system of congruences. Which means we're left with this guy right here, x being congruent to 2 mod 3. So let's see what we've done. We've taken these three, for which Chinese remainder theorem did not apply, and reduced them to these three where the Chinese remainder theorem does apply. So let's write these over here. We've got x is congruent to 1 modulo 4, x is congruent to 2 modulo 3, and then finally x is congruent to 3 modulo 5. So if we solve this, there's a good chance we solve the congruence we started with, although we'll obviously have to check that at the end. Okay, so let's work through this. So we've got our capital N will be this product 4 times 3 times 5. Well, notice 4 times 3 is 12 times 5 is 60. So there we've got that. And then our N1 will be 3 times 5 is 15. Our N2 will be 4 times 5 is 20. And our N3 will be equal to 4 times 3 is 12. And here I'm using just the standard setup that this is like our number A1 little n1, A2 little n2, and A3 little n3 as built in our proof. Okay, so now we've got these 4 important numbers. Now we're ready to calculate our x1, x2, and x3. So let's recall that our x1 is congruent to capital N1 inverse, so that'll be 15 inverse modulo little n1, so that'll be 15 inverse mod 4. But let's notice that 15 is equal to 3 mod 4, so this is 3 inverse mod 4. But then 3 times 3 is 9, which is 1 mod 4, so 3 is its own inverse. So we have this is 3 mod 4. So let's see, in the end, we see that our x1 is equal to 3. Now let's continue. We know x2 should be congruent to n2 inverse, which is 20 inverse mod little n2. So that's mod 3. Let's go ahead and reduce 20 mod 3. So that's going to be 2. So here we need, this is 2 inverse mod 3. Notice 2 times 2 is 4, which is 1 mod 3, which makes 2 its own inverse. So this is 2 modulo 3. So let's see. That means our x2 is equal to 3. Now finally, let's calculate our x3. So our x3 should be capital N3 inverse, that's 12 inverse, modulo little n3. Notice our little n3 is 5. Again, we can do some simplification. Notice that 12 is 2 mod 5. So that means we need 2 inverse mod 5. 2 times 3 is 6, which is 1 mod 5. So that means 3 is that inverse. So we have this is 3 mod 5. So let's see. That means x3 is equal to 3. Now we're ready to calculate our final value of x. Remember, that's going to be a1 n1 x1 plus a2 into x2 plus a3n3x3 by the constructive proof. Now, I'll let you guys do the arithmetic. All the numbers are on the board, but what you end up with is 233. But we know our solution should be unique modulo this capital N, which is 60. So that means we can reduce this mod 60. And if we do that, we're going to get 53 mod 60. So let's just reiterate this 53 by the proof of the Chinese remainder theorem is guaranteed to be a solution to our congruences up here. Now we just have to check that it's actually a solution to our goal congruences over here. So let's see if we can do that. So let's notice that 53, if we reduce that thing mod 4, well, what do we get? Well, we're going to get 1 mod 4. And that's because 52 is a multiple of 4. So we're good to go for this first congruence. Now let's reduce that thing mod 10. We'll notice we get that is most definitely 3 mod 10. And that's because 50 is a multiple of 10. So we're good to go for that second congruence. And then what about mod 15? Well, notice that 53 is 8 more than 45. 45 is a multiple of 15. So that makes 53 congruent to 8 mod 15. So we just checked that this indeed worked. Okay, so let's maybe get rid of this and I'll give you guys a couple of warm-up exercises. So here's some quick computational warm-up problems so that you can test the strategy for the Chinese remainder theorem. So here we've got a system which is x is congruent to 4 mod 11 and 3 mod 17. So here we've got a system of 4 congruences where x is 0 mod 2, 0 mod 3, 1 mod 5, and 6 mod 7. Okay, that's a good place to stop.